Welcome, everyone. It's a great pleasure to have with us here today, remotely, Yoshinta Setyawati, who has recently finished a PhD at the Max Planck Institute in Hanover and is now a postdoc at Utrecht University as part of the Dutch NICEF collaboration. She will tell us about enhancing gravitational waveform models through dynamic calibration. Go ahead.
Thank you, Ofek, for the introduction, and thanks for the opportunity. As Ofek said, I just recently moved to the Netherlands in Utrecht University, so I also want to share a little bit of photo of Utrecht here. This is the botanical garden near our university building. It's very nice at the moment, but we are still in a lockdown. Um, so I will talk about the our attempts to develop a waveform, to develop techniques to speed up waveform modeling, and so to generate a more accurate and fast waveform models. And most of this work were carried out during my PhD at AEI Hanover with my supervisor Frank Ohme. So to give you a little bit of a motivation, I will start with an analog. So imagine that you're an entomologist. It's a person who studies insects. So your main interest is insect, in this case, a butterfly. And there isn't a rare butterfly that you want to study. Interestingly, this butterflies only comes during the final World Cup, in this case in 2018. So you sit there um, among the audience and with so very loud noise, so very loud people supporting, and you have a tool to spot this butterfly. Yeah, and then um, um, you look for this butterfly where the place where you sit um, uh, with these tools. So in this case, in this photo, actually, I have butterfly, and I just Photoshop it. So if you maybe find it, just let me know. I give you a little bit of time to look where the butterfly. Just speak out if you find. Then where is it about?
Bottom right, just above the white line.
Oh, you find it easily. Yeah, not many people can find it easily before. Okay, thanks. Yeah, that is true. That's the red circle. Um, what I will talk later on has nothing to do with butterfly, but that is just an analog about the gravitational waves, and this is from the two compact binaries from the two black holes. They are orbiting each other. When they come closer, when they're about to collide, they emit a gravitational wave, gravitational radiation. And then here's the detectors or the tools that we have is the interferometers. It's an L-shaped interferometer, so the angle between these two arms, they are 90 degrees, and each arm is 4 kilometers long for the LIGO interferometer. And this gravitational wave is squeeze one direction and stretch the other direction simultaneously. So our tool here is that it has a laser beam, and then it's split it into two different arms, and then this laser beams bounce back and forth through a mirror here and then collected in the detector here. So in the case of no gravitational wave, the light from both arms cancels each other, so we don't see anything. But when the gravitational wave passes by, one arm is shorter than the other, and then so you see there is a fringe pattern. So what we do is that we analyze the data from these detectors, and I show you again that here's during the O1 and O3. Sorry, I should explain what's O1 and O3. It's the observing run. So each observing run lasts for a couple of months to around a year. And then the way it works is that we have O1 and then lasts for a couple of months, and then we're not observing. We're in the commissioning phase.
Okay.
Technical pro dropout. We'll wait to see what happens here. Oh. Probably a cable just pulled out of place.
Is it in your side or on her side?
I'm connected to you, but you're next door to me. So let's see if we actually have people connected from outside the campus.
Well, I'm here, I'm still in Ireland, so.
John is in Ireland, yeah.
John in Ireland. Okay, so it's not an Irish problem and it's not an Israeli problem. Probably we've pinpointed the problem to the Netherlands. Okay. Let's see.
You can stop the recording right now.
Yes, yes. Go on, please.
Okay, sorry. Yeah, during O1 and O3, we detect approximately around 50 boundary black holes, or 50 events of boundary black hole coalescence. So I show you this illustration again. This is binary black holes orbiting, and then here's the photo of the Virgo interferometer. This is 3 kilometer each. One arm is 3 kilometer, and it's located in Pisa in Italy, and it normally works in a interferometer network, so LIGO and Virgo. And so from here we expect to get the data and then we learn the origin of the gravitational wave signal. And here's what we expect, that we get the data smoothly like this. However, in reality, this data is buried inside this noise, inside the detector's noise. So yeah, it's not that easy, and therefore the way we do it, we used to do what is called match filtering. So we filter this data with many waveform models that vary with different parameters and different parameter range, and then from there we compute, we do the calculation with Bayesian, also with the best likelihood to get the to estimate where the origin of these waveforms, the origin of this gravitational wave signal. Okay, so so far I talked about the motivation of this study, so I will continue with a brief overview of waveform modeling, and then the enriched basis is the techniques that we try to develop, and then we assess also different regression studies that are important in waveform modeling, and then summary and conclusions. So here's the another plot of binary black hole. When they still orbiting each other with some distance, is called the in-spiral. Is the analytic, we can approximate this with analytical post-Newtonian expansion. And then when the amplitude start to increase and then go to the maximum amplitude here, this is kind of intermediate area into merger. So what is called merger, what we define with merger normally is the peak of the amplitude. And then after that, we have the ring down. So in this case, this area from merger, we use numerical relativity. They're known as good to approximate this area, which I will explain about this later in the next slide. Now let's see that these parameters of the waveforms. So the shape of these waveforms depend on different parameters. So these are in the intrinsic and extrinsic parameters. 1 to 4 is the intrinsic. They are the parameters of the binary itself. In this case, I use mass ratio, where M1 is greater than M2, and then dimensionless spin parameter, eccentricity E. There is another study on this, but I don't talk in this opportunity. And the tidal parameters lambda is only for binary neutron star. In this case, it's only 3 for this black hole. And then the extrinsic parameters are the parameters from the binary relative to the observer. For example, the distance, sky localization, inclination angle, time of coalescence, phase of coalescence, and orientation. So especially in the study, we use the definition of inclination angle is the angle between the binary relative to the observer. So if I focus on the intrinsic parameters because actually we can scale the extrinsic parameters. For example, if we want to model binary for further distance, then we can scale the amplitude of the binary. To illustrate this, I have there is a link here. You can take, you can click. Sorry, you can't click anyway. Maybe you can type it manually. Sometimes it takes a bit of time to load, and I'm still developing this. But this is a waveform visualization. I hope you can see. I'm not sure if you can see the web that I showed you. Please let me know if you can't see.
Well, I'm trying.
I'm sharing another page with the web. Okay,
Yeah.
I will share again. Can you see?
Yes, now I see.
Yeah. Oh, sorry. Close this. Here's the different. This one is in analytic time domain. If you change the mass ratio, they will also change. If you change, in this case, this is eccentric model. So if you change the eccentricity, you can see that this shape also change. Also for the amplitude and the phase. In this case, I also have different. I put different models, different waveform model, and these models are what we use in the LIGO algorithm library, and some of them are used in the analysis of gravitational wave data, the LIGO data.
So this is like a Python interface for running all of the Lao suite choose TD or choose FD waveforms?
Yes. Yeah. Yes.
Cool.
Yeah. I think I should stop share and then share again my slide.
That's a cool link. If you can send it, like email it to us later. It's
Sure.
quite a neat one.
Sure. Thanks. Okay. Please let me know if you can see my slide again.
Yes.
Okay, cool. Yes, so yeah, so this different, as I said, the different shape or different parameters affect the shape and the length of the waveform. To summarize, I want to categorize waveforms our waveform models with these three groups. The first is the analytical waveform. Is like the for example is the one example is the post-Newtonian approximation, the expansion, where this is the in-spiral, the focus on the in-spiral regime. So it is like a long formula. You can put this formula in Python, and then you can easily generate the waveform. So it's very fast. Maybe it's within seconds. But around 1990s, we learned that this post-Newtonian approximation is when the binary moves faster towards merger, this approximation breaks down, and therefore it has less accuracy, especially if we compare to the next group. So another way to solve the vacuum Einstein equation is the numerical relativity, which was around 2005 when it was first firstly generated around 2005. So it solved the problem in around lead in spiral to ring down regime, and has a better accuracy there. However, it's computationally expensive because it solves the problem numerically. It's sent to we solve it in the computer cluster, supercomputer, and so. And then it also takes a lot of time. So for comparison, it may take weeks, months, or even 1 year. It depends, of course, on the number of parameters you use, on the resolution that you use. Of course, the higher the resolution, then the better the accuracy, but also takes longer time. And also big data. It needs big data, so also for like storage. Yeah, so the therefore numerical wave simulations are the number of this NR are relatively few number available compared to analytical waveforms. So the third group is the in-spiral merger ring down, or IMR waveforms. It tries to work between analytical and numerical waveforms. So it is faster than NR. It's expected to be faster than NR, but also better accuracy than analytical. The way it works is that in some model, the way it works is that it use the in spiral, they use the analytical, they use the post-Newtonian, and then they combine it with the merger and ring down from the numerical simulations, and they join that which is called the hybridization. So they fit the function to join these two regimes. And so some of these models have been calibrated to a finite set of NR waveforms. However, if we have more NR simulations becoming available in the data, then we need to recompute the fitting functions, and therefore it needs human resources for this IMR model. So let me go to the enriched basis waveforms, which aims to dynamically update any waveform models. And we expect that this method has a better accuracy compared to analytical, but also faster than numerical, spine weight, parameter range, and also less human dependence. To give you another illustration about this method is that we have, let's say we have two different waveform model. Waveform A is like analytical waveform with characteristic of fast, less accurate, but also dense. And then you can generate it anywhere. If you see here the blue, the purple color that's flat here. And then waveform B has a characteristic of numerical waveforms. So it's low but more accurate, but also only a few numbers are available with these red triangles. The gap between these two is the illustration of the overlap. So the further the gap between these two, then the less the overlap between these two models. So what we want is that we want to develop the green circle here, where the accuracy and the time is always between the target and the basis. So if you, for example, if you want to generate a waveform with this parameter close to here, close to the red triangle, then it will have a better accuracy to NR. But if you have this, then if you close enough to the basis waveforms, then it has better accuracy to the waveform A. However, we want to guarantee that this new model will always have a better accuracy compared to a basis and target, or waveform A to waveform B. In this case, we employed classic mathematical trick to singular value decomposition. The main benefits that we want to reduce the data storage, also faster to generate the waveform, good accuracy, and this SVD actually has been used, also has been applied in industry, for example in Netflix, to for this purpose. So a brief introduction of these. We arrange the data in the matrix form, for example, matrix H, and then we decompose this data with U, sigma, and Vd. This is two orthonormal matrices, U and Vd, and then sigma is what we call with the singular basis. So these are singular values. So the singular values is make it easier because it's sorted from the highest or the most dominant to the less dominant singular values. So in this case, the U sigma is the projection of these original waveforms, and then if we want to return it back to obtain our original waveform back, then we project it back with the Vt with the right singular vector or the basis transpose.
Yoshinta, I'm a bit rusty on my linear algebra. Are there any requirements on the matrix H? Does it have to be symmetric, Hermitian, real, or can any matrix be decomposed in this way?
As far as I know, it's not. It has no. I mean, for the shape, you don't have to be like square, like 6 by 6 or something. Like 6 by 200 is also possible, of course. And then it has to be real, as far as I know. Especially in this study that we use Python is also easier for these real numbers.
Okay.
Yeah. Oh yeah, and please let me know if you have any question. Just interrupt me anytime. So in our case here, we peg our waveform that varies with various parameters in a matrix form. So in reality, these are just numbers, but I want to illustrate this so it looks like a waveform. Okay, we arrange like this, and then we decompose it with a SVD, and then I also plot this U and sigma. Instead of numbers, I plot this like this, and then this is what we call with the projection coefficients mu, and then this is the Vd is this right singular vectors, and the way we do that is that we use the projection, we interpolate the projection coefficients depending on the parameter the desired parameter we want to generate the waveform. So once we interpolate this, and then we project it back with a set of the basis transpose. So this is how we prepare the data. And this is the parameter space. The x-axis is the eta, is the symmetric mass ratio, and the y-axis is the chi effective. This is the spin effective from this equation. And we place our data, our analytical waveforms with the cross, with the blue crosses points, and then the red circles represent the target waveforms. In this case, because numerical waveforms are slow to generate, so we use IMR phenom D to replace IMR to replace the numerical simulations. This is a proof of concept for this study. This is a proof of concept. And for the analytical waveforms, we use IMR phenom B, so the odd version of IMR phenom D. The main difference is that they both have they both are aligned spin waveforms. Only that the main difference is that this is three-dimensional, where chi1z unequal to chi2z and unequal to chi effective. But IMR phenom B is two-dimensional, so they make it equal. Chi1z, chi2z, and chi effective. And then the mass ratio range between 1 to 18. And here's the corresponding symmetric mass ratio eta. And we use the full spin effective and total masses of 50 solar masses. We can always scale the amplitude with total mass anyway. So this total mass has less contribution in this case. Okay, so once we prepare the data and displacing, we use the regular grid. Then we decompose the data with the amplitude and phase. And again, I show you, instead of number, I show you the picture of amplitude and phase in a matrix form. So this is in frequency domain, and here you can see the amplitude, and then you can see the phase, and then we employ this singular value decomposition. As I said before, we decompose this to two orthonormal matrices and one singular values, take the dominant one, and then compute the projection coefficients, interpolate, and then project it back to the with the basis transpose to generate our new waveforms. The overlap between two waveforms is following this formula. So this is the overlap maximized over time and phase shift. And in the left plot, this is the overlap between the original target and the original basis. So in this case, IMR phenom B and IMR phenom D. And if you see here, the overlap or the match between these two waveforms range between 0.38 to 0.99. However, when we applied this method with the projection and then interpolation, and then so we get the result, we compute the overlap between the new waveform, which we call the enriched basis waveform, against IMR phenom D. And the match is now between 0.98 and 0.999. So I think it's I was really happy when I got this result. But however, we want to develop further to get a higher overlap. So in this case, we continue with the iteration. So before I go there, let me explain about this iteration procedure. So in this case, we take the enriched basis, so the waveform that we generate through the procedure before. We take this as the basis for the next iteration. And then so we do it for many times until some tolerance is achieved. So here's the result after some iterations. The y-axis here is the mismatch, is 1 minus overlap, and then the blue line here is the median of the mismatch, and the yellow area is the minimum to maximum mismatch. So it gets better and better with more iteration, but of course after some time it's flat. And this improvement is that how many magnitude lower from the mismatch between the original target versus basis in comparison to the last enriched basis waveform or the new model against the target waveform. So following this, the improvement is getting better and better after more iteration. I think similar to this, the ROQ, the reduced order quadrature, use the iteration procedure. Okay, so turnout is not only a projection that can develop better waveforms. We learned that the interpolation method is also plays an important role to develop a better model. So in many other waveform models, they have various regressions or various interpolation. Some of them are just ordinary, like something that is common, but some other they really develop a new regression or a new technique to interpolate the data. So in the second study here, I want to give you an overview of this regression. The background is that main binary black hole waveform families adopt some regression techniques in this code. Regression plays a key role, especially in waveform modeling. And I raised this question whether more complex techniques means that we get a better accuracy, and in that case, and then it's slower, or maybe that's not. And then how's about the regression for higher dimensional data? At the moment, we have 3 dimension or 7 dimension because of the spin, the 6 spin components and 1 mass ratio. But then if we include more parameters, for example, eccentricity, or if we include or for binary neutron star, if we include the tidal parameters, then we have more dimensions in the data. So how these different techniques will tackle this challenge? That's what we want to ask in this study. So it aims to compare performance and computational costs of various regression methods. In this case, we explicitly compare methods. Here we list linear interpolation, polynomial fits. They are pretty much standard methods that you can also find in Python, or maybe in some other language also this built-in method. Greedy multivariate polynomial fits. This is specially developed in this study from Lionel London and Edward in 2019 for the merger ring down area QNM. Tensor product interpolation is also specially developed by Michael Purer for the reduced order modeling method. especially for EOB family. A radial basis function, you can also modify. There's a built-in function for this, but you can also modify. Gaussian, and then these two machine learning methods, Gaussian process regression and artificial neural networks. Of course, this too depends on the kernel too. So in this study for the artificial neural networks, for example, we use only two hidden layers. So the way ANN works is that you have input, you have hidden layer, and then you have output. So the more hidden layers that you have, then the more complexity you have, and mostly then it corresponds to longer computational time. So if yeah, and then other than that also depends on the nodes or the neurons. So if you have more inputs or more you have more neurons on that, then sometimes it also takes a longer time. So in this case we take almost the minimum one for the hidden layer so that we can compare with other methods also regarding the timing. So to set the data, to prepare the data, we have two different systems. The first one is the aligned spin waveforms, or with 3 dimensions. And the mass ratio is between 1 to 10, and we use full spin, so only the z direction. And the precessing or 7-dimensional waveforms, the mass ratio is quite narrow, between 1 to 2. This is because some of these methods, as I said, is only developed to specific waveform model, and then we want to make it comparison, so we follow the parameter range of this model. And so the full is also follows the full spin range, and we take only the dominant modes, or L equals 2 in time domain. We generate 2 waveform models as EOB and RV3. That is the EOB, that is a precessing waveform from the EOB family. And then similarly from the phenom family, IMR phenom PV2. We place the training set in random uniform training set, and then also random uniform test points. And then we use the correlating frame. So correlating frame means that if we have a precessing waveforms, we transform it such that we can use such that the angular, so the L component is aligned. So the orbital angular momentum is aligned to the total angular orbital momentum. And of course, we decompose this with the amplitude and phase, 2 key parameters. And then we investigate 2 cases. The first one is in the early in spiral, because this is smoother. And then the second one is around -50 m in the late in spiral. So the second case has it has more fluctuations in the waveforms. So we want to compare with less and more fluctuations for these different regression methods, especially their accuracy and computational costs. So well, what we this is, I show you the results from the regression methods that we use. So the N here is the number of the training data set here. So there are more training data here to the right. And then here's the model, IMR phenom PV2 in the bottom panel, and SEOB and RV3 in the top panel. And then the error in percentage for the first panel, and the second, the middle one, is the training time in second, and then the last one here at the right is the execution time, also in second. So this color bar is only the show you the number of neurons used in ANN, where we plot only the best results. So in this case, we also experimenting with different numbers of neurons in ANN, and then we take the best one, and then we plot here, and then here's the color bar of the number of neurons that is the best that we put in the plot. So for the 3D case, I think we can see that this is not the more complex waveform, the more complex technique doesn't always give you the better a better result or a faster result. Now let's go to the 7-dimensional case. This is the processing model. So with higher dimension, there are not that many changes that like some models are you can't see some models here because they are not available for higher dimensions. So the maximum of dimensional parameters in some models are only 3, for example. So yeah, again, but I want to highlight here that this polynomial fit, although it's not that complicated, it's already well known for quite long, but they can produce quite good result and quite fast, if you see also from other panels. I think this is interesting in that in the regards that it's not always that something that is complex always give better results or faster results. In the same paper, we also summarize the different methods and disadvantages. We also give the ready to use references or also code used in these methods. And of course, from another paper, we refer there, and also we summarize what actually the bottleneck of these methods that makes it longer. For example, for linear interpolation, it only needs regular grid. So if you have a random if you place it randomly, then it maybe it won't work. And then training time here, if you have more training data, then it takes longer time to produce the interpolant. Also similarly with the tensor product interpolation, and some methods, for example, GMVP, that's also how the time to produce the interpolant also depends on the error tolerance that you set, and also the basis function. Polynomial degree for polynomial fit, and then also for radial basis function and GPR. For ANN, it also depends on the number of neurons, hidden layers, and also maybe the way to train this. So the method that you use to train this ANN. So okay, that's for the regression studies. I go to summary and conclusions that the new techniques are being developed to speed up waveform generations, to analyze gravitational waves data, and then what we aim is higher accuracy waveform, and then swift to generate, cover higher dimensional parameters, span broad parameter range, but also minimum storage. That would be ideal. The choice of the training data, there depends on the choice of the training data, and then the placing, whether it is grid, and how you group how you group the training and your test data set, and then mathematically the projection, not only the projection, but also the regression method that you use. More complex methods do not always yield a more accurate and faster results, and accuracy can be traded with speed. And another message that I want to give is that we should critically evaluate performance of the approximation methods and the features that are necessary for the data of interest. So it doesn't mean that one big, for example, for the regression specifically, like you cannot one work. Machine learning always work, for example, or for always work better than the other methods. It also depends on your data and your aim of study. Okay, that's all. Thank you, and let me know if you have any questions.
Thank you, Yoshinta. Any questions? See, you got Hebrew on your list of thank you notes.
Yeah.
I wanted to ask, so what kind of use are you doing with these results now? I guess for LIGO or for other Virgo or other analyses, is it going to replace the existing waveforms, aggregate existing waveforms? Is this going to any analysis for either searches or PE?
So at the moment, I'm working on the ROQ. Is to the reduce, maybe you already know, the reduce order quadrature for the parameter estimation, where this iteration procedure is used, and I think it's also depends. There are two. Sorry, I should see again. There are different. Either we use a singular value decomposition or greedy. In this case, there is also another one, is greedy CPP. Okay, so that may be more practical thing, that is the iteration is applied there, but also the there is a package for this method, and it is at the moment it's not used yet, it's still being developed, and so it's more in the waveform modeling phase, where we the more waveform modeling field, where we kind of like make it automatically. Like if you have a set of data, then we how to maximally group it into training and test data set, and then update this with the for example with NR waveforms. I hope it answered your questions.
Yeah, thanks. Anyone else? Going once. Going twice. Okay, thank you, Yoshinta.
Thank you.
Good to see you. We hope to sometime have a physical visit, either for you to come to us or for us to come and visit Utrecht.
Yeah, I hope so.
Good health to everyone.
Thank you.
Thank you very much.
Bye.
Thank you very much.